All right, so one more thing we can do with valence electrons. We had looked at the noble gas shortcut for an electron configuration where we're shortening the core electrons, all the inner orbitals that are nice and full and stable, and we're just showing that as a noble gas, just the symbol in brackets, and it shortens up the configurations quite a bit. And then we're really just showing the electrons in the outermost shell, the valence electrons, and they're the most important. They're the electrons that determine the physical and chemical properties. And we said they're the electrons that are involved in bonding and chemical reactions. Really, it's the electrons that are most important when it comes to reactions, but of all the electrons, we're really concerned with the ones on the outside of the atom. So another way that you could show valence electrons is with something called a dot structure. And maybe you would have drawn these in a previous science class. They're really simple little diagrams that show the symbol of an element. And then around the outside, we put dots to represent the valence electrons. So this little table here shows a section of the periodic table. It looks like elements maybe going across the third row. So we start with number 11, 12, sodium and magnesium. If I wanted to write their shortcut noble gas configuration, we could go backwards to neon. We could put neon in brackets, and then all we have to write is whatever comes after neon. So it shortens it up by 10 electrons. So I only have to write 3s1 and 3s2 behind the neon for the electron configuration of sodium and magnesium. Then if I wanted to keep going across, I would have aluminum, which then would put 1 electron in the 3p, and silicone would have 2 electrons in the 3p, and so on. If I keep going across, eventually I would get to argon, where there should be 18 electrons. 10 of them are in the shortcut noble gas configuration. By putting neon's symbol, we're representing the electrons of neon, which there are 10. And then we would just have 3s2, 3p6. And so the valence electrons are in the outermost shell. The outermost shell here is going to be the third, and all of the electrons in the third are considered valence, regardless of what kind of orbital they're in. So for example, obviously sodium just has 1 electron in the 3s orbital, and magnesium only has 2 electrons in the 3s orbital. So sodium and magnesium each have 1 and 2 valence electrons. But then when you hop over to the p block, we want to count all the electrons in the third energy level. So something like aluminum has 3 valence electrons. There's 2 in the s, 1 in the p. And eventually, by the time I get over to argon, there are 8 valence electrons. There are 2 electrons in the 3s orbital and 6 electrons in the 3p orbital, for a total of 8. And so another short way that you could show this is with the dot structure, where we try to show the dots to some extent how they would maybe exist in the real atom, that if you just had 1 dot in a 1s orbital, and it just shows the 1 electron. And you could put that dot anywhere technically around the sodium. So you could put like sodium. You could have the dot on the right-hand side. You could put the dot on the left-hand side, on the top, on the bottom. It doesn't really matter as long as you have 1 dot on sodium. If I have magnesium, we give it 2 dots. There are 2 electrons in the 3s orbital, and we typically put them on opposite sides of the magnesium, just kind of to show that there would be 2 electrons in the s orbital, but because electrons are both negative, they'll repel and they'll try to orient themselves as far apart as possible. So most of the time they really would stay like on opposite sides of the nucleus. Eventually then I get over to 3 valence electrons. I would have 3 dots on my aluminum. And again, it doesn't really matter how you draw them. And you could put aluminum. And you could put them in kind of like a little triangle. I guess that's kind of what they're showing in their picture. Typically when we get 4 dots, we show them like kind of top, bottom, side, and side, like silicone. And then something kind of interesting happens when we get over to 5. So maybe you've drawn these before and you kind of did like pairs of dots. Well, here we're going to try to kind of mimic the orbital diagram. So if I were phosphorus, and let's say I have my orbital diagram. 1, 2, 3. So this is the 3s orbital, and these are the 3p orbitals, which there are 3. And then I start filling them with electrons. Okay, so yeah, we would have to fill 1, 2, and then technically when I get up to higher energy orbitals, we're supposed to fill them 1 electron at a time. So here would be the orbital diagram for the valence electrons of phosphorus. Do you kind of see how that's similar to the dot structure? That there would be 2 electrons paired, kind of like the 3s. And then there technically are 3 electrons that are single. And so we kind of try to show that here too. That there's a pair and then there's 3 singles. Then when I get to sulfur, sulfur's supposed to have 4 electrons in the 3p orbitals. So before I can go up to higher orbitals, I would have to finish filling the 3p. So do you kind of see how these mimic each other a little bit? That the orbital diagram would have 2 pairs and 2 singles, and so does the dot structure. If I went to chlorine, I would pair 1 more, so there would be 7 valence electrons organized as 3 pairs and 1 single. And then obviously then when you get to argon, you would have all orbitals full. And so we won't do a whole lot with the dot structure right now, but eventually when we look at bonding, we'll definitely bring back this concept of a dot structure, because it's going to help us to like kind of pair atoms together and predict their bonding, where I can draw these dots and kind of see, okay, would these dots be compatible with these dots? But it's just another way of showing the valence electrons, because they are the most important. They're on the outside of the atom. Question 32 looks at patterns, cross-cutting concept. Recall that elements above and below each other in the periodic table have similar chemical and physical properties. Yeah, they do. So like all of the noble gases are gases, and they're all non-reactive. All of the, elements in the fluorine family, fluorine, chlorine, bromine, iodine, astatine, they have really similar properties. They're pretty reactive, they're non-metals. They're asking me here, what do you think might account for these similar properties? Okay, well, we've just said that electrons are responsible for properties, especially chemical properties and some physical properties too. So could there be something similar about the electron structure of elements that belong above and below each other on the periodic table, like within a group going up and down? Well, think about this. So here was my orbital diagram for the 3s and the 3p electrons. What if I did the 2s and these are the 2p's? What if these are all the 2p orbitals? So what if I were looking at the second row across the periodic table, where if I were looking at the valence electrons, in the second row I would have lithium. That would end 2s1. So here would be like the outer electron of lithium. Then beryllium would have 2 valence electrons. They would just be in the 2s. If I hop across to boron, there'd be 1 valence electron in the 2p for a total of 3 valence electrons. And then we would keep going across. I would be boron, here's carbon, and then nitrogen. Nitrogen kind of looked really similar to my phosphorus. Remember phosphorus? Let's see if I can take out some of these guys. I'll make my eraser teeny tiny. Whoa, I didn't want to do that much. There we go. So if I kind of like bloop, and bloop, and bloop. What if I do that? Obviously my boxes kind of went with it. But here would have been the electron configuration of my phosphorus. So this is phosphorus. This is nitrogen. Look at that. They're the same. The valence electrons, the electrons in the outermost shell, are exactly the same when you have elements that are in a group with each other. Now, the only difference is just the distance from the nucleus. So in nitrogen, we're filling the outermost 2s and 2p, whereas in phosphorus, I'm filling the 3s and the 3p. But otherwise, the arrows in the boxes look exactly the same. Think about like sodium versus lithium. Sodium's configuration, if I go shortcut, was neon. And then it just ended 3s1. Think about like lithium or potassium. What if I go one less? I'll go potassium. If I go down the group. So potassium, if I want to go back to the previous noble gas, it would now be argon. And then I would have 4s1. Rubidium would end 5s1. Cesium would end 6s1. Elements in a group going up and down the periodic table have similar electron structures. It's just that the electrons become farther and farther from the nucleus, but it's the same number of electrons in the same types of orbitals. What do you think might account for these similar properties? Are you thinking electrons? I am. I'm thinking electrons, and maybe most specifically the valence electrons. Valence electrons are the same. We have the same number of valence electrons for all the elements in a group going up and down the periodic table. If I wanted to do the dot structure, for example, of nitrogen, it's going to look exactly the same as phosphorus. Nitrogen still has 2 electrons paired and 3 electrons single for a total of 5 valence electrons. It would be just like phosphorus. The only difference is that those valence electrons are a little bit farther from the nucleus, but it gives us really similar physical and chemical properties.